All right, welcome back. Good to see you guys. Hope everybody had a nice Thanksgiving. It was pretty lonely this last class without all of you here. We've got to figure that out. I don't know why they don't just give you guys the entire week off. It makes no sense to me. Hopefully, if you weren't here, you got a chance to check out the topic. We'll review it a little bit. I do want to mention a couple of things, though, because we're getting very close to the end of the semester. So if you have outstanding assignments, I'm not going to grade anything and everything until after the final is due, which is actually the 14th, so that's next Saturday. You need to have all of your assignments in, all your quizzes. I'm going to be completely merciless and give you zeros if you don't have them in by then. So I wouldn't wait until the 14th because you might have technical problems with something not working. Your upload might not work. If you give me a Google Drive link without permission, I won't be able to give you a grade for your final. So do all this stuff earlier than you think you need to. That would be my recommendation. You also need to get your creativity projects in if you want to do it by then. Questions about that kind of nitty-gritty business stuff? Everybody's all good? Yes, please.
So the final is due on the 14th. There was something in the syllabus, I don't know if this has just changed at this point, but it was like the final would be due on the Friday.
I think I updated that. Yeah. Was it the creativity project or?
Maybe it is.
Yeah. All right. Well, I will not grade anything until Sunday or Monday, but I have to turn in grades, I think Monday by midnight. So I only have 2 days to watch everybody's videos and it's a lot of work. So once I start doing that, I'm not going back. So just make sure that everything is absolutely there and that you've given me, again, make sure I have permission to watch your videos because that'll be tragic. I can't be chasing you around about that. So yeah, get it in by Saturday, please. And if your grade is not where you want it to be, do an extra credit project, please. Save yourself. Questions, concerns? Is that a hand up? Oh, okay. Sorry, I thought you guys. I saw a little bit of this from the background. Okay. All right. I think that's it. If you have videos that are outstanding, remember you got to email me so that I know they've been turned in. And then also remember, the grade that you see in Moodle does not have zeros for the quizzes that you haven't turned in. So if you have not turned in quizzes, that is not actually your grade. Be warned. Okay, I think that's it. Everybody, please do the work, get an A, live long, be happy. Who was here last week? Who remembers what we talked about that we could embellish on a little bit and catch people up who missed it? Any memories? I know it's been a whole week. Yes. Yes, please. All right. Oh, what's a Kahoot? Oh yeah, yeah. Okay. That's not very creative. I think you could do better. I already did that. You mean like in-class questions, like things that aren't in the textbook? That'd be kind of creative. Yes. What do you want to do with them? I mean, look, every single person in this classroom, I guarantee you, has something weird that you guys do. And you do basket weaving or knitting, or you write short stories, you write poems, you draw little pictures, you make cartoons. Every single person has something like this. And that's what I want you to do. Do something creative with it. All right, beautiful. Upload it. Yeah. No, it's an extra credit project. It's an addition. It's an option. Yeah, I just uploaded it to Moodle this week, but I've been talking about it all semester. There's not much more to say. It's kind of completely open-ended. It's worth up to 8 points, I think. Final project's worth 15, so it's worth a lot. But if depending on how much effort you put into it, I'll give you commensurate points, basically. But yeah, people have done all sorts of crazy stuff in the past. Everything from time-lapse photography projects to short stories and poems, everything in between, paintings. Also, somebody baked like a solar system cupcake set one time. That was pretty crazy. I'm sure they were tasty. I didn't eat any of them, but everybody seemed to like them. Yeah. How about we good on that? All right. What's that? You're not gonna do Kahoot? It just has to be creative. That's all. Outside the box. All right. Who was here last time? Who remembers anything at all about what we talked about? So depressing. All right. Well, really, I know. Come on, Shay. I know you were here at least. You remember something?
Yeah,
Rolando, it's you.
I'm trying to, like, I just don't really have anything that, like, expands on anything we were talking about.
That's okay.
We have a lot of other classes.
That's a weird excuse. Why do they get priority over this one? Okay. Yeah, actually, yes.
I do remember that we were talking about like the mythology
Of Uranus, right? Yeah, that was a weird one. I actually left. My wife and I were talking a lot about that and trying to come up with some sensible interpretation of it. Nasty, do you remember what your interpretation? First of all, Shay, you were right, and that like Gaia is involved in this, and it's like this huge, elaborate. It's really the central myth, as far as I can tell, is about Cronus, who is Saturn, and Uranus kind of plays like a ancestral role in that. And but yeah, there's something very strange about. See if I can remember this. Gaia is married to Cronus. No, Gaia is married to Uranus.
And they're the parents of the Titans.
And the Titans get involved in this, that's kind of beyond my understanding. Like it gets up when we get into several generations of Titans, I get sort of lost. But for some reason, Uranus convinces one of Gaia convinces Cronus, who is a son, Gaia's son, with Uranus to castrate his father. And this castration process, because I guess the father, the sky god Uranus, has done something tortuous to the other children. He's like locked them in a dark cage or something like this. And then this castration process results in the birth of Venus. And I'm like, what in the heck is going on there? I'm sad to say that I haven't figured it out myself.
Yeah, it's hard to derive symbolic meaning from that, like, because I think it's so far removed from our daily lives. Like some of the myths we can derive meaning from because it also relates to our daily lives. But like ancient people just starting to figure that stuff out, I think it could be that. Like they were just kind of
There could be some of that, I think, yeah.
figuring out how to take control of or like I don't know, like keep
There's also this whole
time or agriculture or something like that.
right? Because this is the thing that happens is that Cronus, the one who castrates his father, ends up inheriting the throne of the universe, right? At the end of all these Titan battles and stuff. I don't know what happens there, but a golden age comes on, basically. And Cronus is, of course, associated with time and order. And so you get this idea that maybe there's some memory or some reflection upon the way that society is structured somehow. I don't know. That's about as far as I can get with it. But yeah, the more I dug into that myth, the more complicated and crazy it got. So I don't know. I'll keep working on it. But
The restrictions of the father are the grounds of his own destruction. But the seed of the father is then the seed of the
oh,
and so like the fruits of the father has to be destroyed. You can't get away from the fact that the fruits of the father is also the seed of everything.
and how does that play out in the modern world?
interesting if you think about like cruelty being replaced by like,
Hmm.
yeah, like cruelty being giant. I mean,
Yeah, I know. It's
like,
kind of.
like war and deprivation and all of these things are like in some ways the sins of the father, right?
I don't know. I don't know.
And then like out of order flourishes.
Peace. Yeah, because it's supposed to be a golden age that Cronus brings on, right? Which is this peace and prosperity time. We're kind of in a golden age in some sense right now. It's like the least amount of war that the world has ever seen right now. Is really?
I think that all cell phones are
Far out. Yes.
Often think about nature portal. It's like this Instagram page that I used to look at.
Interesting.
It's just like a page that just shows like their common traits.
Just like destroying people's houses and
No, it's usually animals.
like eating each other and stuff.
Like that,
Yeah, I think that there is some sort of memory of human beings having gone through some transition like that. Because even if you just watch chimps, like it's super brutal out there. And they're what 99.9% the same genetically as human beings. So there's there's something strange that we made a pact with when we developed this whole civilization thing, whatever you want to call it, society. And that must have been a big deal. That must have been a heck of a moment, or several moments. I don't know. So yeah, I think these myths capture that, and the Uranus one is perplexing amongst them. But I don't know. I'll think about it more for next year. All right, what else? We were talking about Uranus, Neptune. They're kind of some of my favorite puzzle pieces. So for the people who weren't here last time, one of the more interesting things about these worlds is that they, unlike the other gas giants that y'all were here to discuss, these ones have really complex molecules in them. So they're called ice worlds because, generally speaking, they have these condensed forms of volatile molecules that would otherwise be evaporating, like methanes and ammonias, water, stuff that, generally speaking, if you put it out in space, it would just turn into a vapor. But because it's under such intense pressure in these weird planets, it exists in some sort of phase which is more close to a liquid or an ice than it is to a volatile gas. So they're not really gas giants. Now, originally, all these planets were considered gas giants. But now we know they're not, any of them are gas giants. But these guys are more complex. And so the formation story, like traditionally with these, was like a little bit trickier because you had to, in order to condense really complex molecules, you had to do it far away from the sun. If you're going to have this story where everything's born in place, like the Laplace story that we've been kind of trying to repair for 300 years, you have everything form, you have to have these things form really far away from the sun. The problem is, if they form really far away from the sun at the same disk velocity as everything else, they fly off the leash really easily. So it's been this really interesting problem trying to solve how you get them to perhaps form far away, but then move in long enough that the orbits can stabilize and they can give some of their momentum off to the other planets, and then maybe they move back into place where they used to be. You end up with this really complex story. And so we're investigating this other idea that's been appearing on the edges of the scientific landscape lately, which concerns the transition of Neptunes into mini Neptunes into super Earths, which basically happens in one of two ways. Either, and I got some pictures here, so either the atmosphere gets blown off by the sun, so you cook down something that looks like a Neptune into something that looks like a mini Neptune and then eventually into a super Earth, or as essentially the core from being compressed contributes to the cooking off from the inside. So as it loses some atmosphere naturally, the core decompresses, and it's been very hot since it was compressed, sort of like gas in a diesel engine or something like that. You actually have a great reservoir of heat underneath us. Now, we have that in our own planet, too. There's a lot of heat underneath us, presumably from its formation, compression, and so forth, whatever that story happens to be. So you have several mechanisms by which you can cook off your atmosphere. And the interesting piece, of course, of these Neptunes and of these Uranuses and so forth is that they seem to have a rocky world already buried at their core. And what's really intriguing about that for me is that it gets you out of the pebble boulder accretion problem when it comes to describing or explaining where rocky worlds come from. In a Neptune or a Uranus, you have plenty of compressive power to squish pebbles together and make them molten and actually get something that looks like these really dense rocks like the one we're standing on right now. So it's an intriguing story. There's I found a couple of other pieces too. If anybody wants to tackle this idea for your final project, this one's in Quantum Magazine, which is pretty cool. I can give you the link if you want it later. But it's kind of about the crumbling line between planets and stars, which is a related idea. This is talking about all those free-floating Jupiter-like planets detected by the James Webb. And then there's this other article I came across that talks about what I was just explaining with the Neptunes, many Neptunes, and super-Earths, and the different mechanisms by which this, they think they're observing this happening in other exoplanetary systems, let's say. So, I don't know. It's interesting when we consider all these formation models. I think that's the most interesting thing about the Uranuses and Neptunes. And if you think about all of these mechanisms, they don't have to necessarily be at odds with one another. So there may be situations where you do form a Neptune really far out in the middle of nowhere, and it is this situation where it accretes a ball of volatiles out there. Maybe that thing over time, it manages to grab up a lot of asteroids and space junk and stuff and crush it down into a core and ends up becoming a useful planet or moon at some points in a completely different system. It gets cast off. In biology, we have this idea that there's two ways to evolve, right? You can evolve a structure because you inherited it from the people before you, essentially, or you can adapt a similar structure as somebody else through a completely different mechanism. And I think we should be open to the idea that both of those things happen. Remember, like bugs have wings and birds have wings, but birds didn't evolve from bugs, or bugs didn't evolve from birds. They both came up with the wing because it solved a problem similarly, or we could just say because they're reacting to similar environments and they had similar needs. I think the same thing could be happening with a lot of these planetary formation systems as well. So, something to consider. Thoughts? Anybody? Planetary evolution? Yes.
So I guess this is kind of related to these articles. So is this kind of suggesting that instead of these, what we would usually call rogue worlds, instead of them basically leaving a solar system, that they would have formed on their own outside of a solar system?
Yeah, exactly. I mean, you have two possibilities for that. Either they got flung out of either the standard model of solar system formation in situ, things accrete out of this protoplanetary disk. Either that works and these planets got kicked out and then established new orbits around each other, which is pretty far out by itself. And then that can get you down a whole rabbit hole of can a solar system grab one of those? Are solar systems actually mishmashes of different formation processes? Like maybe Jupiter formed in a different solar system and then we just ended up with it, right? So that's really interesting. But also just the idea that maybe you actually get the formation of planets outside of solar systems altogether. That's far out too. Like either way that you go with it, that observation just begs for some revision of this simple formation paradigm that you have a disk, the planets form like little condensed droplets out of it, and that's the whole story. It's like, I hope you guys are starting to see that doesn't hold up. That's not going to hold up much longer, as far as I can tell, on account of this data, in this article, but also, the problem with rocky worlds being as dense as they are and so forth.
Why? I guess, it doesn't seem that far-fetched that you would have planets being formed without a solar system. Why was that not previously something that was I mean, maybe it was thought of before, but it obviously has not been widely accepted.
Yeah.
Why is that?
That's a great question. I'd be open to hearing why people think that, but I think as best I can tell, the basic story we got for once we realized that we had a solar system and they weren't just a bunch of gods or whatever. Very shortly after the Galilean Revolution, people had to come up with a story of how this thing got, like how it came together, right? And so people had the figure skater idea of, spinning, swirling systems and all this, and they'd actually observed what they called spiral nebula at the time. Spiral nebula turned out to be galaxies. They did not know that until very, very recently. They thought the entire universe was our galaxy, actually. And so I think they were just trying to come up with a story that made sense. And then what happens is once everybody comes up with a story that makes sense, it tends to get grandfathered in generation to generation. And people get really comfortable and used to it, and they move on to other problems. As opposed, like, this is a really interesting thing that we've been tackling a lot in the rest of my life, with Dr. Benneberry and just in general. It's like, how is it that we make these big mistakes in science all the time and then just move on? And it's like, I think it just becomes the water in which we swim. Like, we're fish, and we're just swimming in water, and we don't really think about the fact that we're swimming in water because it's just, that's our world. And there's a lot of encouragement. Like, if any of you guys go to grad school to do your PhDs or anything like that, you'll very quickly find yourself completely like face down in the trenches working on some tiny little problem. The last thing on earth you're going to have time for is going back and thinking about the fundamentals of the assumptions that you've been handed in your discipline. It's like you're going to, even if you go into planetary science and like you have like big ideas of getting around to studying this kind of thing, you're still going to spend 8 years or however long it takes you to do your PhD building like some detector for a telescope to get some piece of data that's going to contribute to a big paper with like 30 authors on it. And like, it's a very, the institution is enormous and slow moving, and everybody has very specialized roles in it. And so we get really far down the road until we come to a point where we point our telescope at the Orion Nebula and we're like, oh my God, like there's planets without solar systems. That's weird. There's no star, and these planets are orbiting each other. Like, we should probably rethink this whole thing. Or we see exoplanetary systems that, have planets which are, most exoplanetary systems, we'll talk more about this next semester, but most of them have all the same kind of planet in them, right? They either have a bunch of super Earths, they have a bunch of mini Neptunes. They're all very homogeneous, and we don't have one that's homogeneous. So that's really weird. Maybe it requires thinking about how this thing got put together in the first place. So, I don't know. What do you think?
No idea. I don't know. What I'm thinking about right now is the fact that we have this idea, like how much mass does this account for? Because I'm just going back to that, we have this idea of dark matter, and really just idea it's matter that we can mathematically account for through the gravity, but we can't physically see it through light. Or is this like, are these planets the answer for that?
Maybe.
I don't know.
Yeah.
That's where my mind is.
Yeah. I have a friend who's smarter than me, and he thinks that's the case. There are arguments against that. This is something we'll unpack a lot next semester too, but seeing things that are cold and don't give off light is darn near impossible. So you're restricted to looking at like lensing events or something transiting in front of something. But yeah, you can make something really dense, i.e. very gravitationally influential, that's really tiny, right? Like think about our Earth, like it's a pretty significant piece of material crammed into a tiny little place. I don't know that if our Earth say our Earth evolves 5 more billion years in the future and it doesn't have an atmosphere and it's cold, I don't know that you're going to be able to see that from a few light years away, right? So that's a reasonable proposal. And I think there is probably some part of the dark matter without getting completely in the rabbit hole of dark matter right now, that's probably part of the puzzle. There's some other ideas too. There's probably more to a galaxy than just gravity too. And so, there's a lot of places to start looking. One of the things that they've just started studying, and I mean like 2 labs in the whole world, is the organization of galactic magnetic fields, which is really fascinating. It turns out they're really, really complex. It's not some simple magnetic field like the Earth. There's different sheaths of magnetism. It's really, really complicated. But there might be something in the electromagnetic world involved in sort of gluing these things together too that we're just not accounting for. I'd be interested in seeing all that developed more. But yeah, there's a lot of potential for missing stuff. Also, a lot of the estimates for how much stuff could be out. Oh, this is another reason I've heard that this theory that you advanced poo-pooed is because people will say, well, to get a bunch of cold junk out there, it would take a really, really long time, right? And we're not permitted those kind of lengths of time that it would require to cool things off to that degree, based on the popular cosmology of the day. Now, it's worth pointing out to you the popular cosmology of the day a mere 150 years ago would have been that the Earth was 6,000 years old. Oops, sorry. So we've come a long ways in 150, 200 years about how old the universe is, the Earth, let's say. We might come a long ways in a short time as well. So there might be plenty of time, depending on how all of this next generation telescope stuff plays out and the model of the Big Bang and all of that. It's like really funny because a lot of people will say, especially next semester, this semester I've been really picking hard at the edge of where I think things are going to shift, where the next paradigm shift and all of this is going to come, which I think is the evolution of planets. Next semester, it's the Big Bang. And so people are often like, who cares about the Big Bang? Why does it matter? This is why it matters, is because the stories we tell about our Earth, the stories we tell about the formation of the planets, all those things are constrained by the timetables that the Big Bang gives us. And what's really weird is the Big Bang is essentially constructed by a bunch of mathematicians off of 2 pieces of evidence, essentially. And so that's a really weird situation where you don't have this proliferation of evidence to support something. You have 2 pieces, a bunch of mathematicians who aren't part of any of the other sciences, but they hold the keys to the castle of all of the other sciences that we're concerned with in these discussions anyways. Everything from planetary formation, earth sciences, atmospheric sciences, climate sciences, astrophysical stuff. Like, it's all constrained by the cosmologists, which is just a really, really weird bottleneck situation. So yeah, the Big Bang matters for all of these things, and this is exactly why. So yeah, I don't know. I think there might be something to that, though. It's not the first time I've heard that theory. I don't know if there. Thoughts, anybody? All right, if anybody has thoughts as we go along, please shout them out. I was going to take the rest of today to sort of check out the moons of some of these giant planets that we've talked about, primarily Jupiter, because most of these giant planets have really similar moons. They kind of follow an archetype a little bit. There's sort of a format to them, and I think it's worth looking at. They have also a little bit of silly, preposterous formation stories associated with them that are essentially the same as the Laplacian story. Usually it goes that each one of these giant gas planets had some sort of disk of gas around it when it formed, and then the moons just sort of plopped out of it. That's pretty difficult for me to swallow personally, especially considering the density of these things, for the same reason that we've already beat to death with the planets themselves. So a lot of these planets are solid rock. They have iron cores. Sorry, did I say planets? A lot of these moons are solid rock. They have iron cores. And so they're quite interesting specimens. And I think that we can also imagine a formation mechanism for a lot of those that follows the similar thing to the Neptunes and so forth, where you have a big ball of something that squishes the rocks together at the center of it. We also, one of the things we're going to notice too as we go through all these moons is that a lot of them have really weird orbits, right? It's like, okay, if all the moons had formed in place out of some sort of circumplanetary disk of gas and debris and stuff, you'd probably expect them to be sort of all in the same plane of rotation, at least, all rotating the same direction for the most part, and all having similar spin tilts axes, right? I mean, maybe one of them got whacked or something, so you could forgive a few moons having their spin axes tilted or something. But the opposite is actually what we find. In general, we find hundreds and hundreds of these little moonlets, most of them quite spherical, many of them too small to have become spherical under gravitational influences alone. Many of them orbiting the wrong direction, clusters orbiting the wrong direction, many different groupings of them. So you'll have groups going here, groups going here. You have all sorts of orientations of these moons. It really speaks to a highly variable capture story to me, where you're swooping up moons. And it's like, well, where did the moons come from if you didn't swoop them up from your own circumplanetary disk? They must have come from somewhere else. So in some sense, the story of moons, I think, is a continuation of the paradigm shift that's unfolding for the rocky planets in general, which is very evolutionary as far as I can tell. So let's talk a little bit. Obviously, as we get further away from the Earth, we have less to say about the moons because we've spent less time there. One of the things I think I mentioned last time for those of you who weren't here was that I believe we've been nearby Uranus once. Basically, every time you take a step away from us, you've explored it less and less and less. So the moons we know the most about are the Galilean moons of Jupiter, which are the big four. You can see them, and I'm going to spend probably the most amount of time on those. I want to talk about Saturn a bit, because Saturn's the next one out after Jupiter, and Saturn's got these crazy rings too, which we should play with a little bit. And then we'll talk a little bit about the ice giants and Pluto if there's time, but again, very little to say about those guys because we just haven't been there yet. It's kind of funny also, there's a bunch of objects beyond Neptune. They're called trans-Neptune objects. Pluto used to be a planet, now Pluto's just another trans-Neptune object. Turns out there's a bunch of these things that are on the order, on that same size scale order, so they all just get kind of lumped in together. And we know very little about them, so they won't get a lot of our attention today. This is kind of interesting because these are the four moons that you can see with a telescope. Actually, this is what it'll look like if you go out with a telescope, essentially. You probably won't get that crispy of a view of Jupiter, but even if you have binoculars, I highly recommend it. You can just, if you have binoculars, you need to stabilize your arms like on a windowsill or something like that, or get a tripod, even better, if you can, like a camera tripod, and clamp them onto it. But it's super profound. I can't recommend it enough. It really changes the way that you feel. There's something about seeing the actual light from the stars with your own eyeballs. But anyways, when Galileo first turned his telescope out to the sky, this is what he saw. And so Galileo actually wanted to name the moons after his sponsors, which is kind of hilarious. It's like, can you imagine if we were like naming the newfound star systems like Pepsi and Starbucks and Coca-Cola and whatever. But yeah, they decided to name them, of course, after more Greek and Roman gods, as usual. So these guys are the four that we'll really fixate on today. And they're all a little bit, they're similar in some ways, but quite different. Io is a really, really weird one. I don't know that there's anything like Io in the whole solar system. It is super, super bizarre. And that's the one I guess we'll turn to first. It's let me go back to the picture of it. It looks kind of like a stinky cheese of some sort. It's very sulfurous and very magmatic. It's got all these volcanoes all over it. It's really weird. So it has all of this internal burbling, which is plenty of convection and all of that stuff, but no magnetic field, which is really weird and sort of jeopardizes our magnetic field narrative that we tried to construct earlier. The other ones are very icy worlds. I think for the most part, they're thought to have subsurface oceans, and we actually have a few missions planned to go and check those out, which we'll talk about. But Io is a really weird one. And Io, it turns out, contributes to the construction of Jupiter's magnetic field as well, which is a kind of wild story. These moons are also, they're in a really tight resonance with one another. So in other words, each time I have another picture of this later, but each time, one of the early ones goes around, the other one goes around, the interior will go around twice maybe for the next one. And so they have this real musical harmony to them where they're stabilized by this because they get extra kicks that hold them in place. And I think this is important because, one of the questions when we start thinking about why does our solar system look the way that it looks is because the things that were here that weren't in these nice resonant patterns probably got lost a long, long time ago. So when we start asking those questions like, why is James Webb seeing I think in that study from that article that I listed there, they found 500 worlds in this one little place where they pointed their telescope, 500 rogue worlds that they found. Why are there 500 planets without solar systems? And it's like, well, that's what natural selection looks like a little bit, I think, honestly. Why are there only 4 Galilean moons around Jupiter? Well, there may have been a lot more. They may come and go, but these ones seem to have stabilized themselves through this resonance process. And so you get these chains of resonance where essentially each time one moon goes around, it kind of holds on to the next one in the line. And they form these really stable ratios of orbits and keep themselves in place. And this you see a lot of this resonance in this solar system. You got a question?
Has there been any sort of like frequency detected, or we're just looking at these numbers and like recognizing music within it?
Yeah, it's a little bit of a analogy more than anything. So it's like, the number of vibrations of a fundamental tone to its overtones is what we call notes in music, basically. So they're resonant relationships, you have an octave would be like 2, it's vibrating twice as fast as the original, so 2 to 1, right? And you can expand that and say a perfect fifth is defined as 3 vibrations to 2. The same sort of thing is seen throughout the solar system. You have these ratios of vibration being the orbit, right? The period of how many times it takes to go around. So it's a little bit of an analogy, but it is a genuinely resonant system, just like a string on a violin. You get overtones, you make notes out of it. I mean, the early astrophysical natural philosophers, like people like Newton and Huygens and just all the original people that we kind of talked about the first few weeks, those guys were obsessed with the fact that God had made a musical instrument out of the sky. They saw these resonant patterns in the orbits and everything, and they were certain that it was done for a purpose, right? Because music was this divine expression of the cosmos, and that of course the cosmos would be playing out these musical pageants. And so they refer to it as the music of the spheres. And I think there's a very famous, is it a Vivaldi symphony called Music of the Spheres? Anybody know this one? No?
I don't know who composed the symphony, but there's also a book
Okay.
that it was based on.
Oh,
Um,
I love that you know this stuff. It's awesome. I feel like you have a better grip on some of these esoteric matters than me when it comes to
I just
the-
read one article about the music of the spheres one time before this class, and I was like, oh,
I think I had to play it in high school band of some sort or something like this. Yeah. Anyways, they were obsessed with it. People absolutely, these scientists absolutely believed that it was a divine phenomenon. I think that the reality of the situation is that the reason that the notes, first of all, it may be perfectly divine. I'm not trying to take away from that. But when you talk about resonant relationships in music, what you're really saying with resonance is that you have a tone, which is a series of waves, and then you have another tone, which is a series of waves. When the peaks of those waves overlap, they reinforce each other, and you get a louder tone. And so certain combinations of frequencies are going to result in more amplification, and that's going to be a kind of beautiful thing to us, essentially, because it's constructive. And I think the same thing happens in these orbits, right? They get kicks, it stabilizes the orbits, they last longer, and so they populate the sky in our experience.
I find it interesting that they're all A in different octaves except F sharp Callisto.
Yeah. I don't know how they pick the fundamental, the scaled frequency. I'd have to go and read this article a bit more. System-sounds.com, check it out. Yeah, I wonder how they pick the fundamental frequency. Because that seems kind of arbitrary to me, but maybe it's not. It's funny though, because if you just go through the solar system or through any of these moon systems, they all have these resonant chains like this. And they might be, I don't think that humans use a 12-5 note in their scale. I could be wrong about that. It might be some microtonal structure in like Turkish guitar playing. I have no idea. Like it might be a thing that people do, but generally speaking, our Western scale is constructed almost entirely out of fifths. And so we've kind of reconstrained our picture of which combinations are useful for making music. But I know different cultures have gone far beyond that before. Anybody ever microtonal music? Anybody? No. Okay. What's that?
That's the opposite.
It is super complicated. I mean, these guys have like frets in between their frets on the guitar and stuff. It's wild looking. All right, so let's check out a few of these moons. They're actually quite interesting, especially Io. I think the story of Io is the most interesting, and I don't know where the heck Io came from or why it's so weird and different, but it is really interesting. Particularly in its role in constructing the magnetic field. Okay, so like I said, I might kind of just plow through this. We talked a little bit about the standard formation model for these. There's people working really hard on rescuing that standard formation model for these. A lot of it is essentially, from what I can understand, it's a combination of these instabilities that accumulate in this gaseous disk and lead to these little accretion modes. This resonant feedback thing starts to pile up. We actually had one of these guys on our podcast at some point. I thought I would just, let me see if this is it. Yeah, I thought I would just play you the standard model of formation. I'm personally really skeptical of this model, but I thought I'd let you guys at least see it so I can give the devil his due.
Jupiter was born within a protoplanetary disk that orbited the Sun during the first few million years of its lifetime, and as gas and dust rained down upon the newly born planet, Jupiter became encircled by its own circumplanetary disk of satellite building material. In time, this disk grew more and more dusty thanks to a balance between headwind and updraft attained by icy dust rains, only about a millimeter in size. Eventually, the ring of dust around Jupiter became so massive that it collapsed under its own weight into thousands of satellite testimals, icy asteroid-like objects, about 100 kilometers across. The orbits of these satellite testimals are shown here as orange ellipses. Over thousands of years, satellite testimals coalesce into moons. The mass of the growing satellites is depicted here with a logarithmic bar chart on the right. As the mass of a moon crosses a threshold, it begins to raise spiral wakes in the gaseous nebula and migrates towards Jupiter, leaving behind a mess of satellite testimals to birth the next moon. Here we see the first two moons, Io and Europa, form in about 6,000 years. As sequential satellite formation unfolds, the orbits of satellite testimals grow more and more excited. Eccentric orbits slow down accretion, and it takes longer and longer for additional moons to form. In fact, Ganymede makes its debut almost 30,000 years into the simulation. Close to Jupiter, the converging orbits of the first three moons stabilize, establishing the orbital clockwork of the Laplace resonance, wherein for every 4 orbits that Io completes around Jupiter, Europa completes 2 and Ganymede goes around once, with the system returning to its initial state every 172 hours. Our calculations show that this celebrated orbital architecture must have been built from the inside out over a timescale no shorter than about 10,000 years. Eventually, radiation from the newborn sun evaporates the gas from the Circumjovian nebula, leaving behind a disk of icy debris and triggering the formation of Callisto. Because of the gas-free conditions in which Callisto forms, its conglomeration takes much longer than that of the other moons, nearly 9 million years. In particular, it achieves about half of its mass in the first 50,000 years, but then takes more than 8 million years to grow the rest of the way. Jupiter's moons are mysterious and fascinating places that contain water, salts, and maybe even the building blocks of life itself. Understanding the formation of Jupiter's moons helps us illuminate the intricate physical processes at play in the solar system's early evolution and unlock some of the deepest secrets held by the planets. Space missions.
All right. So we talked to this guy. So as you can see, 10,000 years to form the first moon, which is pretty extraordinarily fast. That's basically the time between here and the last glaciation cycle. I think a matter of millions of years for some of the others. So this is really, really strange. And they still haven't dealt with the pebble boulder problem either, which is a subject of our conversation. I don't know. It's interesting. Like I say, I think that there can be a number of convergent aspects to this as well, though. I think that the resonance stability, different instabilities that develop in disks of debris and so forth, absolutely can play a role, along with in more radical capture mechanisms too. So here it is. Io, very lovely, beautiful yellow, moonlit. It's actually the fourth largest moon in the whole solar system, and it has the highest density of any moon, which is just crazy. So that thing was, I believe Batigan just said it forms in 10,000 years. That's freaking crazy. But there you have it. Tons of convection in this thing. It's literally getting resurfaced all the time. I'll show you some pictures in a minute, but there are new volcanoes forming every single year. So they tried to go back and photograph a volcano. It wasn't there the next year. A new one had grown up next to it. So its surface is constantly being remodeled. And unbelievable amounts of convection, but nothing approximating its own magnetic field, which is really bizarre because it is supposed to have a similar internal structure to us with the iron core and all this magma and everything that we would expect. So very, very bizarre. This actually, I wish I could offer you guys some theory at least as to how these magnetic fields make sense, but it's one of the biggest glaring open topics in this whole field that we've been exploring this semester together. First time we went there, Pioneer 10 and 11, that was in 1973. Since then, we've been back many times. Late 70s, Voyager 1, Voyager 2 got some more detailed pictures of the thing. 1995, the Galileo spacecraft gave us some of these beautiful images. And actually, we've been back since. I think we were literally just in the neighborhood of this thing. Now, the Galileo mission was the first time that we started to actually be able to get information about what was in these volcanoes that were spewing out into the space in between Jupiter and the moon. And so let me see if I can find one of these pictures. It was really, really crazy. So they started making some estimate of the material here. 2007, we get back with the New Horizons spacecraft and start to get an even more detailed picture of it. And what they find is kind of shocking. So what they find is that Jupiter, for up to this point, had a magnetic field that was far too large for any of the models that they could come up with, right? It extended much further than it should have, in other words. The strength of it, whatever. But it turns out that the junk that's actually being kicked out of these enormous volcanoes on Io was getting ionized as it went out out into space, essentially. And what was happening was that it was becoming sort of like an antenna that amplified the magnetic field of Jupiter itself and extended it far into the distance. So you actually had this strange system by which a moon was acting as an amplifier, much the same way that a solid core inside of a magnet amplifies its effects as well. You have the same process being happened by this volatile ejection from a little moon. Very, very bizarre. Again, I probably should put this earlier, but this is essentially the interior model of Io, which has this iron core, has some sort of magmatic mantle, but none of its own magnetic field still, which is very, very bizarre. Now, when it comes to why this thing is so hot, that's another kind of interesting piece of the puzzle. So it's obviously bubbling over And the other moons of Jupiter are really, really cold, as we're going to see, which is quite bizarre. The explanation that's given for that is that the thing is essentially getting the diesel mechanism, the compressive mechanism, it's getting tugged and pulled by the enormous planet that it's orbiting quite close. And so as it goes around, it's sloshing and compressing this thing, and it leads to its heat. So, the figure that's given is that if you're talking about just decay of the radioactive elements inside of the planet to keep it warm, it gives off something like 200 times the heat that it would get just from the natural decay of its products. Pretty crazy. Oh, here's that picture that I wanted to show you guys. So I think this one picture on the left is from November of '99, taken by Galileo, and the spacecraft, not the guy. And then February of 2000 on the right. And so you essentially see the production of new lava plains there on the left that weren't evidence. It's interesting there's like some darks on these photographs. I assume they just had some dead pixels on their camera or something bizarre. But yeah, the surface is constantly being remodeled, which is interesting. There's also the presence of mountains that they can't explain through volcanism alone, too, which is really bizarre. But nothing in the realm of plate tectonics, nothing in the realm of magnetism. So a very, very weird piece of the puzzle, the magnetic field puzzle. Here's a picture of one of those plumes. Let's see, this is from, I'm not sure where this picture is from, but you can actually see up at the top one of those volcanoes just spewing its contents out into the space between Jupiter and itself. Now, it's kind of hard for us to imagine how big these volcanoes are, right? We've had a few really bad eruptions. Maybe there's been one in our lifetime that was pretty enormous. None of those were kicking stuff into space, so to speak. Now, Io has a very tenuous atmosphere compared to us too, so that probably has a lot to do with it more than anything. But they're enormous eruptions. I wish I could give you a direct comparison. Like the plume of this is 100 kilometers tall. So the surface, generally speaking, what do we consider? Like the surface of our own atmosphere to be like 60 kilometers maybe up. So these are serious volcanoes, and they're constantly appearing. All right. Thoughts, questions? Anybody? Keep going on our tour.
Is Io, is it tidally locked with Jupiter, or is it, you're talking about these forces that are acting?
Oh, that's a really good question. I would guess it is. Yep. I've heard people advance the idea that a good definition for a moon would be that it's tidally locked. Yeah. So yes, it is. So that fits. I guess that explains why it's getting squozen. Yeah, and I'm not sure what its period is off the top of my head either. We could look that up. The period of Jupiter, like what is Jupiter's rotational period? And I'm guessing that it's out of sync with Jupiter's rotational period, right? Because there's some sort of inhomogeneity inside of Jupiter itself, and so it's going to get different amounts of gravity depending on where it's at in its orbit. I won't look that up right now, but I'm assuming that's to be the case. All right. Let's check out a couple of the other guys here. We'll just go through a couple of archetypical ones. So Europa is another one that's quite interesting. Europa is the subject of a number of missions that are going on right now. I believe it's the JUICE mission and the Europa Clipper mission. There's a European Union mission and a NASA mission that are going on right now. It is the smoothest surface of any known object in the solar system. It's kind of cool. And it very stereotypically, as we look at a bunch of these moons, it has what we think is a subsurface ocean on it. And so that makes it a very intriguing point of study because, of course, following all those origins of life conversations, salty geysers and stuff like that are really intriguing to the possibility that they might harvest. I think what people would really like to see is life originating in real time. Like they would love to see proto-life stuff. That was like when Dr. Benry was given her talk, that was kind of the crux point. It's like, okay, how do you go from these little, autonomous or these isolated cells of chemical reactions to something that's moving under its own volition? That moment would be, I think, the origin of life and the exobiologist's dream of witnessing that happen. And there's Europa's a perfectly good candidate for something like that, but as we'll see, many, many, many of the moons throughout our solar system have these subsurface oceans, and they have geysers and cracks in them and things that would lend themselves to another shot at the roulette wheel of viewing something like that. So there you have it compared to our moon, which is kind of interesting. I think these moons in general are, the moons we're going to talk about today are comparable in size. 16th largest moon and 15th largest in our object in our solar system. It's actually the least massive of all these Galilean moons, and has a similar density to everything else, like the thing very close to what we're standing on, the terrestrial planets, Mars, Venus, Earth, mostly comprised of silicate rock with some sort of core, iron-like core, very similar to us. It's got this really weird surface structure that people haven't really nailed yet. They don't totally understand how this happens. The best attempts at trying to explain how it gets these weird surface crack features is that if the axis was tilted at some points rather violently, that you would get kind of these like wrinkles would form as it fell into a new tilt position. Of course, how in the heck, why was it tilting? What's going on? What would do that to it? Could it have, I don't know. I mean, could it have spent time in different locations? Would it have had ways to invert its tilt based on that? It's kind of hard to understand. At any rate, poorly understood, but quite beautiful, strange surface features. What else can we say? It's another view of some of these crustal features. Very, very bizarre. So the interior, like I said, is very prototypical. We're gonna see this crop up over and over again. It's got this outer layer of water around 100 kilometers thick, which is quite an ocean, by the way. How deep is our ocean? Does anybody know off the top of their head? What, like at its deepest point, like 5 miles or something like that? So maybe 10 kilometers? I don't know. 100 kilometers is a heck of an ocean, though, needless to say. And then, of course, there's this thin-ish crust on the surface that covers that from view. And there's a number of models about what that would actually look like. What do we have here? I mean, people are hopeful that there's going to be these warm geyser things down at the bottom. Occasionally, I'm not sure about, on Europa, there's actual cracks, I think, at the South Pole, where you see some of this water vapor spewing out. And so the thought is that it must be being warmed from down below somehow. So either it looks like there's two models here, and either there's some sort of convecting ice-like stuff, which is basically just like highly pressurized water of some sort that's convecting a little bit, or you genuinely have a true liquid ocean underneath the ice that's been warmed enough by its interior, and just the outer layer is kind of frozen over and insulates the rest. People have no idea. This is an image that was actually taken. It's obviously an color enhanced image, but you can see down there on the South Pole some of these little. This is actually an image taken by the Hubble Space Telescope, which was our previous generation telescope before the James Webb. And you see these plumes which are reaching like 200 kilometers out into space. It's like 20 times the height of Everest. Really, really nuts. But again, seems to be kind of common, actually. And that, in some sense, is the grand hope for these exobiologists. People are really hoping, I think part of this Europa one of these missions, either the Clipper, I don't have it in front of me right now, one of these two missions that's on its way over there, is in some sense to try and taste those plumes and figure out if there's any organic molecules in them. Although organic molecules are not necessarily a sign of life, they would encourage further search, I think. One of the ways we get organic molecules is the decay of living organisms. Seems to be other ways, as if we make it, I think we'll make it out there, if we make it to Saturn's moon, Titan, we're going to see tons of organic compounds, but nobody seems to be entertaining the idea that it's leftover fossil remains of dead organisms, right? So you can get methanes through geologic processes, it seems, which has actually been a really interesting paradigm shift in my own life. When I was a kid, everybody talked about petroleum products and these like energy dense polymers as being fossil fuels, and almost nobody uses that word anymore because they don't always come from fossils, it turns out. So yeah, we'll hopefully get a taste of that thing. Yeah.
One of the missions is supposed to drill into the crust of Europa. Like, how is it going to drill down far enough to get to the ocean?
Exactly. Yeah, there was this is a little image of that explorer that somehow drilled down. One of the best ideas. So I don't think I gave you I don't think I advanced exactly how thick that ice layer is. It's very thick. It's like 10 kilometers thick or something. Maybe somebody can Google that for us really quick. The proposal is that you essentially take a big radioactive furnace and sit it on the surface and just let it melt its way down to the bottom. Pretty cool idea on its face. Obviously, loading a bunch of nuclear materials onto the nose of a rocket is a reasonable call for concern. So I'm not sure that anybody has immediate plans for how to pull that off. That's one of the big tricks, with nuclear waste and with nuclear materials in general. Is like they're really powerful and useful, but they're also really dangerous. So the cryobot and the hydrobot, interesting. They're also very concerned with these missions too. Yeah. Wow. 20 to 25 kilometers. I mean, I don't think that there's any drill that we have on Earth that's capable of doing anything like that. I could be wrong about that, but can you Google one more thing for me? What's the deepest hole we've ever drilled on Earth? Let's figure that out. Yeah, that's going to be really tricky. Another thing people are really concerned with is how do we know that whatever organisms, say we go there, we go through this, Herculean effort to drill our way or melt our way down there, and we are like, oh, we've got some bacteria. How do we know for sure that those aren't bacteria that we brought with us? Because all of these other missions that we've done sample returns from, they do show signs of contamination. Even the moon, when they brought back rocks from the moon, they found signs of staph on the moon. And so nobody was thinking that the moon was infected with bacteria. They immediately were like, no, this is a contamination that happened. But how do we know that in the future? How do we ever, aside from just seeing a mat of bacteria growing on a rock, is the molecular detection of bacteria going to be really convincing to people? Especially if it turns out that evolutionary mechanisms are so conservative that even when life evolves on a planet 1 trillion miles away from here, it essentially looks exactly the same as it does here. It's not out of the question that could be the case. You might not see extremely different signatures necessarily. So, I don't know. These guys have their work cut out for them. Did you figure that out? Okay, that's not bad. that's not bad. But it's not 20. It's not 25 or whatever we say. Yeah, but it's also on Earth. It's a lot easier to. Yeah, that's hard to imagine. Wow, 12-kilometer hole that they dug. Where was that?
Somewhere.
Yeah. Only the Russians are hardcore enough to dig a 12-kilometer hole. Amazing. Okay, so if we keep going, there's a couple more of these moons. They're honestly they differ in some ways, but they're very similar. They have a similar kind of structure to them, let's say, from what we can tell. This is Ganymede. Ganymede's actually quite a bit bigger than our moon, as you can see here. There's some interesting evidence, by the way, that Ganymede was observed as early as 365 BC in China. There's a mention of this astronomer named Gan De, who was talking about Jupiter having this reddish companion. Could have been something else, but if you look at Ganymede, this screen is kind of legendarily awful, but it does have a little bit of a brownish red tint to it. All right. And then, of course, we have our resonant chain once again. It's interesting that Ganymede and Bettigan in that video mentioned that Ganymede was in a 4-to-1, and the other one, I think it said 15-to-4, so it's not quite perfectly a 4-to-1. I have a feeling it's not quite perfect. All right, so what can we say about Ganymede? Similar structure. Oh, Ganymede's interesting because Ganymede has a magnetic field, magically. Again, huge mystery. People are fighting over the mechanism by which this could happen. It seems like the state of the art with this argument right now, the best argument that's been put on the table so far is that the liquid in its subsurface ocean is extremely salty and therefore conductive, and that there are some sort of currents that are churned up that do that process that we talked about with the solenoid when we were talking about mechanism. When we were talking about magnetism. So you get something very similar. Again, it's difficult to swallow and hard to make sense of because you have basically the same architecture for several of these other moons who have no magnetic field whatsoever. Magnetism is just mind-bending as far as the solar system is concerned. All right. Ganymede, I guess it's going to also get a flyby at this next mission. So we're looking at the path of the juicy Jupiter. It's called the JUICE mission, Jupiter Icy Moon Explorer mission, which just launched April 2023. Expected to get to Jupiter in 2031. That's a long drive right there. And then it's actually going to enter orbit around Ganymede in 2034. So hopefully we'll all be around to see what happens. You can think back many years from now on this class and see what they find. See if they make sense of this magnetic field. All right, if we go one more out, we get to Callisto. Callisto is really interesting. I guess the one thing I'd like to point out about Callisto, and Callisto, again, has the similar kind of interior structure that we've been talking about, maybe a different layering structure. The one thing about Callisto that's really, really bizarre compared to the other moons is the thing is absolutely murdered by asteroids. It's completely chewed up. In fact, if you try to date this thing based on impact rates and so forth, you come up with like trillions and trillions of years old for this moon. Now, nobody really knows why that happens or why it looks so different, but some of these impacts are incredible. Like this one that I picked out for this picture here is 100 kilometers across, this impact. This is an enormous impact. This is like Chicxulub level dinosaur-ending impact. But it tells a really interesting story that's somehow very different from the other moons that we've looked at so far. In fact, I would say that Europa, Ganymede, like they arguably seem to have a similar history to themselves, but Io and Callisto are just complete black sheep, just very, very weird looking. It's interesting because, this process of determining natural history by inventorying the way that things look has like a rich tradition, right? That's how we came up with this theory of natural selection, and evolution really came from this naturalist approach where you go out into nature and you look at the similarities and differences between bodies, and then you try to construct a story that makes sense about how they evolved along those lines, which is very different than this sort of deductive method by which Bettigan tries to run a simulation where he gets these moons to fall into the right place at the right time. It's like two very different approaches, but on the surface, Callisto looks really crazy compared to the rest of the moons and seems to have gotten itself into a heck of a shootout at some points. You know, the last few minutes here, got like 10 minutes left. I'm probably going to just roll through Saturn and talk a little bit about the rings. Does anybody have questions? Any more questions about Jupiter? Obviously, we ran out of time here, but I hope you guys get a sense of, and the moons, by the way, as we move into Saturn, Saturn has a number of moons. Many of them have the exact same layout as we've seen, with the subsurface ocean, this kind of silicate, rocky, maybe an iron core. It's a very, very common motif. So, again, talking about this evolutionary paradigm that we've been playing out with the Neptunes and them crushing down this rock and creating these little cores. Those little cores are all over the place. Now, can you see a little rocky planet or a moon with a James Webb telescope? No, you can't. You can only see these big, huge things, right? That's why they're seeing Jupiter mass and brown dwarf-sized planets, because those are the enormous things. These little rocks, if you look at the size of a Callisto or an Earth even next to a Jupiter, it's basically invisible. It's a tiny little pebble compared to a Jupiter or something like that, right? And the Jupiters and the brown dwarfs are radiating heat away too, so they're easier to see with the infrared scopes. Some of these rocky things are cold, especially these moons. They look like they've been dead for a really long time. So Saturn's got this ring structure, and I regret to inform you that we don't know why or how long it's been there or where it's come from or where it's going. Many people think it will be gone in the next few millions of years. Yes. That's a really good point, actually. Maybe it's like a size reference. Yeah, that's really funny. Maybe it's actually called the Earth Ring. That's really funny. Maybe it's the name of one of the rings. This is just a diagram because all of the different ring structures have been given names. Hold on, we can figure that out really quick. No, I have no idea. Yeah, there might be a dot there. It's hard to see. Oh, is it? That shows the size of Earth. Oh, perfect. Oh. Why is that a scale, like a scale reference, or it's just showing where Earth is in this picture?
It makes sense, because it looks like this is from the dark side, so it's facing the sun.
Yeah, good point.
Yeah, so it would be Earth would be sun.
So Earth's like in the distance here, in other words, over there.
You can see Earth with a little dot on the photograph.
But it's like in the distance. Gotcha. No one's ever asked that before. That's very, very observant. Yeah. People are always playing with the idea that perhaps the ring's like a broken up moon. That's a very recurring theory for it. But it's troubling because at the same time you have little moons inside of it that seem to be quite evolved themselves throughout it, right? Also, the amount of material inside of this ring is very, very low on its own. This is a very, very, very thin ring structure. I wish I could put a number on that for you right now, but I don't have it in front of me. There's also another ring structure, which is more diffuse. So if you look at this diagram, oh god, it's horrible up here. Essentially, this Phoebe ring structure, the entire Saturn is that tiny little dot over there, this whole Saturn ring structure. And there's a really big diffuse ring structure that's tilted 27 degrees from the other ring structure that extends even further out. So Saturn's got lots of interesting stuff going on and some sort of mysterious history in the past that's difficult to make sense of. Some of these rings are actually being carved out by individual little moonlets themselves. The rings themselves are almost pure water, which is quite interesting. So 99.9% pure water ice. with a smattering of impurities, including little pieces of rock and stuff. So that's really interesting. It's almost like you know, if there was a moon there, the pieces of the moon are gone, and all that's left is its ocean, its vaporized ocean, which is very, very strange. Now, people, obviously the story that Batigan told in that video of Jupiter had it having a huge ring structure at some point as well, from which the moon's actually condensed out of. But I guess that doesn't necessarily fit here because we have some fully developed moons already, unless there was a much bigger ring structure in Saturn's early history. So, what else can we say? Apparently, the rings of Saturn also contain a fair amount of molecular oxygen gas, which is quite interesting. There's like a tiny atmosphere out there. What else can we say that's interesting? This is a really beautiful one. This is a tiny little moon called Daphne's that is carving out a little gap as it tumbles through one of these. Here's another one of those. This is a moon called Prometheus, a little moonlet that's tumbling through one of the rings and carving this beautiful texture through the F ring. All right, I'm going to end on this. Saturn's got a bunch of moons. They're all at different. They're all sort of spread all throughout it. The one that's actually off this picture, I think, is called Titan. Titan is one of the most bizarre moons in the whole solar system, as far as I'm concerned. I will just leave you with. By the way, Titan takes up. This is, I believe, by mass. Titan carries most of the mass of all of Saturn's moons, and it is this very bizarre yellow planet. It's kind of in the same way Io was, except this yellow is by a different mechanism. So if you look at it, it's comparable to the moon again. But when people started making, when some of these, like Voyager made a radar map of its surface, it found that it actually had these very bizarre lakes of liquid on it. And people were like, whoa, that's weird because we've never seen liquid lakes on any body in the entire solar system other than our own planet. And they were like, what the heck is that? Turns out that it was actually a reservoir system of complex hydrocarbons, so methanes essentially, and other chains of carbon and hydrogens, basically. So this was, what year was that? 2004 was when they really nailed this down. This was really the moment, I think, when the fossil fuel word kind of went out of fashion. People were like, holy cow, this happens without biological organisms. Here's a couple of pictures of those methane lakes. Super crazy. I'll just leave it at that. We have a lot of diversity here. The moons are kind of like a zoo. They fall into certain categories. There's another one at Saturn that's beautiful called Enceladus that has a lot of these geysers as well. It's a very common motif. So it seems like there's some conserved ways in which moons come about, but there's also a lot of weird outliers, and it's difficult to tell a single story that holds them all together. So think about it. We'll talk about it a little more, and then I want to talk about asteroids and the asteroid belt and impacts and all of that, and that's how we'll wind this course down. One last class, guys. So I'll see you then, and talk to me if you have any problems with your getting all your final grades in and all that stuff. All right, have a good week.